start our seminar on biomechanics. And I would like to introduce Dr. Truong Ha from Le Quy Don Technical University, Hanoi, Vietnam. And the topic of his presentation is semi-monolithic scheme for simulating strong coupling, fluid structure interaction, and application to hemodynamics problems. Dear Sang, please, you can make a presentation, and after that we will ask something like that.
Okay.
Please.
Okay. Yes. Yeah. So can you see my presentation?
Yeah.
PowerPoint. Okay. Hello everybody. My name is Truong Ha, and I'm from Department of Mechanical Engineering, Le Quy Don Technical University. I'm very happy to here to present a seminar on biomechanics from invitation of Professor Alex. Thank you, Professor Alex. So my topic is a semi-monolithic scheme for simulating strong coupling fluid structure interaction and application to hemodynamics problem. First of all, I would like to introduce some my biography. My name is Truong Ha, and I'm from Department of Mechanical Engineering, Le Quy Don Technical University from Hanoi, Vietnam. And this is some my field of interest, computational fluid dynamics, CFD, and second is numerical method for FSI problem. And the third is high performance computation for computational mechanics by using multi-grid method and parallel computing algorithm. And application to problem of hemodynamics of cardiovascular system, blood vessel in stenotic vessel, heart valve, and coronary artery. And the last one is numerical simulation of aerodynamic heat transfer process. And today, this is the outline of my presentation today. The first is I want to talk some background of fluid structure interaction. And second one is numerical methods. And the last one is some result and discussion. As we know that the fluid structure interaction, FSI, have many important role in science and technology. So like in automatic or wind turbine and airplane, or the important I want to talk today is in blood vessel system. Yes. This is a heart valve, and this is a hemodynamic, and this is a system blood vessel in the human. So today I want to talk about the numerical methods to simulate FSI problem and apply in the blood vessel in the human. So firstly, this is the governing equation. Blood vessel is incompressible fluid flow and can be represented by Navier-Stokes equation. This one V is in equation 1. So V is velocity, and here is W is velocity of grid, because we use ALU, arbitrary Lagrangian form. So the grid is moving. Here and sigma is Newton's stress. For solid is this is the deformation of solid in the Lagrangian form. Here U is deformation, and some quantitative equation here for the, because it's a large deformation, so we have this is quantitative equation. And for strong coupling of fluid structure interaction, we have two conditions. The first is here velocity is equal derivative of the deformation in the interface, and the second one is the stress. Stress is continuity in through the interface. Here is condition for strong coupling of FSI couplung. So in our method, the first is how to show the fluid. So in our method, we use the finite element method for incompressible navier-Stokes, and we use the fractional step method. Correct Nicholson scheme he employed for the temporal discretization of the diffusion term, and Adam Basford scheme for convective term. And the first equation is the momentum equation, where we want to show the V star here. And the second one is we show the pressure equation. This is pressure Poisson equation. And the last one we correct velocity by the third equation here, V n plus 1. For fluid equation, we want to show D here is a deformation, and this is a equation for three components of deformation. Here we use Newton Raphson, because this equation is nonlinear. We use nonlinear. We use Newton Raphson to obtain the linear form. This is a relation of stress and strain. D here is something like the stiffness of the matrix. And if we use the Lagrange, we use Lagrange method to get the linear system. Here is the ZS means the total matrix for solid, and KS is the stiffness matrix, and MS is mass matrix, and can be writing in this equation. So for fluid structure interaction coupling, we need to satisfy the two equations here. The first one is the velocity condition, and the second one is the traction condition. In general, we know that there is two methods for FSI coupling. The first is the monolithic method. It can be called direct method, means solid and structure are shown in one matrix system. So in commercial software in Adena can shown using monolithic. And the second one is the partition method. It can be called indirect method or staggered method. That means solid and fluid are shown in different matrix system. In partition method, it can be split two methods, one-way coupling or two-way coupling. So now Adena or ANSYS can usually apply the partition method. This is advantage and disadvantage of monolithic and partition. Monolithic, we shown because we hold fluid and solid together. This is the method for monolithic, and this is partition. For partition method, we shown fluids first and apply the traction. The second is we calculate traction on fluid surface, and the third is we show structure, and we repeat the process of until conversion. This is the metric of the monolithic and staggered. Advantage of the monolithic is this is more stable and can be used for last time step, but the disadvantage of monolithic is the huge matrix size, and sometimes it's the in-condition matrix can be happen. Also, it's quite complex to program. But the partition method is unstable due to time slip and unstable for last time step. But the advantage of partition is monolithic and the program is easier. So this is the partition coupling algorithm. Here we use finite element method P2, P1. It means that velocity is allocated in vertex and the middle, but pressure only vertex. We use strong coupling partition effect of the density, and we found that the partition method is effect of the density ratio. Here, if the density ratio is around 10, I mean quite big, so the partition method is quite good. But if the density ratio is small, something like 0.5, so the partition method is quite slow. Here, it's quite slow. So here, in presentation, we use a method named semi-implicit monolithic. This is the semi-monolithic algorithm. The first, we shown velocity here, V bar, and we show also V star here, and we update pressure, and the last one we will update the velocity and plus one. Yeah. Semi-monolithic first step is we predict the displacement at interface here, and second one is we create velocity update W and plus one. This is just Laplace extension. And step 3 is we show diffusion and conversion term as the third equation. And in step 4, it is strong coupling partition. So we show pressure and displacement in one equation. The first is Poisson pressure equation, and the second one is displacement. And the step 5 is we update fluid velocity. We use Newton Raphson, so we can show together the first equation for Poisson, and the second one is the equation for deflection, and we can combine in the one system here. So this is called semi-monolithic because we shown displacement and pressure in one equation. For the math update, we use the spring analysis algorithm. Here, equation for math update, because when the grid is big deform, so we need to math update. So this is some benchmark problem. The first one is we use a 2D flexible beam behind the cylinder. This is a grid and some dimension of simulation domain. And this is the movement of the point in the end of bar. So we can find that the semi-implicit cycle time is faster than implicit partition or monolithic methods. Here, the deformation of the solid bar flexible. We can benchmark problem here. So we can see that the cycle time for the FSI3 problem density ratio is 1, and monolithic is 4.2, and partition is 11.8, and we can see semi-monolithic is 1. So the prison method is quite faster, very fast compared to partition method or monolithic method. This is the different grid extension. We use the spring extension and swapping. So after swapping, the grid it look better. This is the second benchmark problem named pressure weight for propagation in a straight tube. Also, we can see that semi-implicit monolithic is faster than the implicit partition or monolithic method. Yeah. And the radio displacement or axial displacement is similar to the result in the literature. We can use a semi-monolithic for hemodynamic application. The first one is a blood vessel, a blood flow interaction with blood vessel in carotid bifurcation in the rat. This is a boundary condition for pressure or Phillips fluid flow rate. Here is displacement and was here says of some point. Here is the comparison of vessel wall deformation obtained by a numerical method and experiment data. Here is shows some velocity vector and the magnitude velocity contour. Next one, we want to simulate the 3D heart valve. Here is aortic valve. It's a 3 lip. This is a geometry and the streamline, and we use the grid here. And the last one, we want to simulate the deformation of the aortic valve. Here is velocity magnitude here, and some Gaussian charge distribution on the valve, and velocity field of flow through the valve. It's line deformation, and also the material is full nonlinear. This is the animation of the wall shear set and also the von Mises set. And we can see the semi-monolithic algorithm can be shown the complexible geometry of the hemodynamic problem. Here is the valve problem. And that is all my presentation. Thank you very much for all of you. Thank you.
Okay, thank you very much for your presentation. Any questions, please? So,
I have a question.
yeah, Professor Vasilevsky, please. Yeah.
Hello, thank you for your presentation. I have a question about mesh deformation. So you showed that swapping of mesh produce the most reliable result. Do you have tangling of meshes for 3D cases? Because in examples which you showed, the deformation of fluid mesh was not large except for the last example. Have you met tangling of tetrahedral mesh?
Yeah. Thank you very much for your important question, Professor Wu. Actually, I present here only first I use mesh update by using Spring algorithm. But on 2D, I use swapping. Yes, swapping only 2D. But actually 3D is quite difficult. So in 3D, I use remeshing. I mean, in the fluid mesh, I use remeshing, not swapping, because swapping is quite difficult. So I use remeshing on 3D, so I can simulate the valve problem here. In the
so you remesh every time step?
No. I remesh every I think 20 time step. I mean, when the skill unit is close to 1, so I remeshing.
Okay, so you use spring analogy every 19 time steps, and then you remesh. What is the time step for this last simulation?
Time step I use 10 to minus 4.
10 to minus 4. So you applied within one cardiac cycle, you applied, let me to compute, 10,000 divided by 10, 500 remeshings, right?
Yes.
Yes, within one cardiac cycle, you applied 500 remeshings.
No, one cycle is 1 second.
Yes.
Means that 10,000 time step.
Yes.
So after 20 time step, I remeshing. So the number of remeshing is.
So it is 500. It is 500 remeshings. So each remeshing which you applied, is it conservative?
Conservative. Because after remeshing,
you reconstruct the mesh. then you have to
Yes.
reinterpolate solution from one time step to another, from one mesh to another mesh. If you have meshes, you have to reinterpolate solution between two meshes.
Yeah, exactly. I use interpolation.
Why it is conservative?
Because I use interpolation method. I mean, will update the velocity and pressure from the old to new grid. After remeshing, I need to use interpolation.
Yes.
I mean, updates from old to new grid. So actually, it's also a little different. I mean, not exactly the conservative, but it's also acceptable. I mean, the solution is convergent.
So what is the interpolation procedure? I don't understand. From two meshes, between two meshes, you produce new mesh and you have solution on the previous mesh. So what is reinterpolation procedure?
I just use a linear interpolation.
But it may be not conservative. You may introduce artificial vortices or something like that. And you do it consequently 500 times.
Yes, maybe. I didn't check it, but
I see, I understand. Thank you very much. I see what happens. And for your valve, for your cusps of your valve, what is the model for each cusp? It is triangulation. This is membrane model, or this is shell model. What is the model, elastic model for each cusp of the valve?
Actually, I understand the point. Actually, the good one is shell model, but in my work, I just use a nonlinear model. I use a monoribbling model for structure. Actually, this
so it is three-dimensional mesh. So it is 3D.
Yeah. Actually,
so it has
3D.
Thickness, it has thickness, and you have a mesh composed of tetrahedra for each cusp, right?
Yeah. I use tetra grid, 3D grid. The technique is 0.5 millimeter.
Mm-hmm. Okay, thank you very much.
Thank you, Professor Lu.
Okay, thank you. So any questions, please? Okay, can you just to return to question of Professor Vasilevsky, show our video with your vortices on last slides, just for me to see how it goes. Can you return please to your slide, to your last slide with video? Yeah, something like that. And could you please, yeah. So did you analyze and compare the vortices that you have produced here with another data, with another results? Or maybe with medical data, with just to validate your results?
Actually, this one I didn't validate by experimental because I don't have the experimental data, so I just show the simulation result without validate. I mean, in future I going to give validate this result.
Yeah, it's quite nice to validate to see how goes it on, what's it, because I think that there are some vortices behind the leaflets when leaflets are open. After, and in this area behind the leaflets, there some vortices observed. So in
Yeah, exactly.
Yes, and I think that also should be taken into account. And can you just say what's an acronym for VMS? What it mean? WS, I know wall shear stress, but VMS is what is it?
Yeah, sorry. VMS mean von Mises stress. Actually, it's a stress on the solid. The von Mises stress.
Von Mises. It's von Mises
Yeah.
stress. Okay.
Yeah.
Okay. Von Mises stress.
Yeah.
Okay.
Stress on the solids. Yeah.
Okay. So, and another question is about, can you show please slide 5? Slide 5.
Okay.
Okay. And here you use two conditions on the fluid structure interface. So it's
Yes.
traction equality on traction and on velocities. But usually in the literature also they use the third condition is displacement. Why did you don't use equality of displacement on boundary on fluid structure interface?
Sorry, I didn't catch the question.
Okay, so
let me to explain. Let me to explain. Actually, the mesh in fluid is continued from solid. So actually, you don't have too much independent displacements of fluid and solid because you don't have displacements in fluid. You need only to construct a mesh in fluid. So actually it doesn't require continuity of displacements because displacements does not exist in fluid.
Actually, this is the condition, but in the implementation, I use velocity for all domain. I mean, velocity of solid and velocity of the fluid. So I applied the velocity of fluid and the velocity of in solid is the same. I mean, I use the same velocity at the interface for precision methods. So this is the condition. Means velocity at the interface is a fluid and solid is equal.
Okay, I've got it. So thank you. And how do you see, for example, the continuation of your project? So you developed this method and apply it to aortic valve simulation. How do you feel? What's the next step for this project?
Actually, the strength of fluid and structure is equality, is continuity in the interface because we just shown fluid and solid it together, and we just combine fluid and solid it together. Here, this one. This is sub-step one is structure, and the second one is solid displacement, and we just combine this one in the one equation. So the state is automatically continuous in the interface. I just combine pressure and displacement.
Okay.
It is automatically certified the second condition. I mean, stress.
Okay, dear Sang, maybe you didn't hear my last question. So you applied your algorithm to aortic valve simulation, So you now you can simulate blood flow in aortic valve. Okay.
Yeah. Yes.
Yeah. How do you see the development of this project? What's the next step? How do you see the project, your project development?
Yeah, actually, in the future, I want to the first is the develop the parallel algorithm, because this is just a zero competition, so the CPU time is quite high. So the next one I want to develop parallel competition, and the CPU time will be reduced. The computation may be a few hours, and I can simulate some complex geometry, something like bifurcation artery and other complex the complete case in blood vessel. Yeah, that is the future of my project.
Okay, so we have one more question in chat. So from Saveli Peshin, and he writes, hello, thank you for presentation. Is aortic valve geometry patient specific? And how did you get this 3D geometry?
Yeah, actually, to obtain the geometry is not my job. I get this from some city image. I mean, other people they get the geometry by using some the CT scan, and they can produce the geometry by CAT. So I use the CAT data to generate the grid for fluid and solids. So and I use CAT data to simulate it.
Okay.
Yeah.
Thank you. Is there any questions?
One more question.
Okay, please.
Yes.
Do you have any analysis of your scheme? Stability analysis or convergence analysis?
Analysis?
Yes, numerical analysis. I mean theoretical.
I think in theoretical it's quite hard, so it's very hard to. Yeah.
Okay, I recommend you to look at our papers. We have theoretical stability analysis of fluid structure interaction schemes. So by the way, we passed all these benchmarks except the last example, which is not benchmark, but all previous examples have been passed with time step 10 to minus 2, not 10 to minus 4.
10 to minus 2? Oh.
Yeah.
How? Because as I know, the solid deform it requires a small time step. I mean, 10 to minus 2 is very big, I think.
Yeah. I tell you, let me to do this. Just a moment. Just a moment. I want to put one reference, and you can download this or check this book.
Okay, it's very good. Thank you.
Just a moment. This is public chat. Okay, here it is.
Okay, I see. I go check it. This one. Okay, I see it. Yeah.
There is, of course, we have another numerical scheme, but by the way, the finite elements are the same. This is Taylor-Hood, P2, P1.
P21? Oh, okay.
P2, P1, yes.
Yeah.
Okay, thank you.
Yeah, thank you, Professor Hu.
Okay, thank you very much. And I guess that nobody wants to ask the question. Thank you once again, dear Sang, for your presentation. Thank you very much. And thank you everybody for being here. So see you next week. Goodbye.
Okay, yeah. Thank you, Professor Alex.
Thank you very much.
Yeah. Thank you, Professor Yu and Professor Alex. See you.